All right, let us continue. So, right, last time we were talking about basically, right, finding the densities of a transformations, right, of a pair of, well, doesn't have to be a pair, right, of a vector, right, of a random vector to another. And basic point, right, is in this formula right here, right, given the old density, right, you can find an old uh, joint density, right? You can find a new joint density by using the old joint density, right? Plugging in the solution, right, of the new variable in terms of the actually the solution of the old variable x, right? This is solution of x in terms of y, and then multiply with the absolute value of the right determinant, right? Meaning the determinant of the inverse direction. Uh, the one thing to remember, right, is this formula is only part of the solution. The other part, right, is about the support, right, of the joint distribution, which is not given, right, in the formula. So, right, this example shows you where, right, if you have a basically a joint independent, right, on a square, then if you do this linear map, right, which actually is a rotation, okay, a rotation. I'm not sure there's a scale in there, 1/2. I think there's a scale as well, rotation and a scale, right? Then you see that the density is 1/2, okay? The new density is 1/2, but that's not the end of the story because 1/2 where, right? The 1/2 actually is on this, rotation, right? A rotated square that's given by these four lines, right? So basically, that is the part that we have to figure out on our own, right? From the interaction between the new variables, the UV with the XY. That's not given, right, by the formula alone. All right. Now, let's take a look at some other example. And one thing, right, that is useful here is the fact that sometimes maybe your interest is only on one combination, one specific combination. Let's say you want to find the sum, right? If you have two random variables, you want to find the density of the sum. But, right, somehow it's not easy. Then what you can do is to go through the transformation of a pair, right? You could find another V that is suitably easy to find together with U. And if you're lucky, you can find another candidate that is independent of U in the transformation. But the point is, right, instead of finding one, you can find both. And then integrate, right, to get the desired answer, okay? And so this this transformation also has that purpose where you basically, right, find a pair and then integrate out to get the answer you want. And so, right, for example, right here, when you have independent on the square, right? So here, the choice, right, to find the sum actually is not about using the transformation formula, but to just directly work with the geometry of the sum on the square, right? The reason is because here, when you have, right, x and y like this, then, right, the line x plus y equals to u can be drawn through with this, right? So this is x plus y equals to u for different values of u, right? So in this case, for example, right, then going through the formula up here actually is too much, is painful, right? Here you can just work directly with the geometrical approach. But this has limited use because, right, it only works with things where you can calculate out the area very easily. If you can't, then, right, this approach doesn't work. All right. So that's really it, right? Basically, the lecture here, right, tells you or gives you a tool to be able to find, right, density of combinations of random variables in a complex way, right? Multiplication, adding, subtracting, whatnot, right? So this topic right here, right, this way, right, especially the certain kind of pair of transformation like the polar coordinate, actually shows up in different places. What I plan to do is to not go through the problem set for this lecture. Okay. The reason is, even though it's very important, it's kind of technical, and the real application of it usually is already done for you, and then you just kind of quote the result. So I want to go through the materials, right, just to make you at least aware of the formula. Okay. But I'm not gonna go through the problems for this problem set. So basically, we'll skip one problem set, right? Problem 9, okay? Problem set number 9. We will not do it, and we'll go to problem set number 10, all right? And your homework and your final exam will cover that, but there will not be any problems from this lecture 9 topic, problem set 9. Right. Any question about this? Okay, so now this one, right, will actually be an important topic that you have to work out things for yourself, and it has more, let's say, more applications than the previous one. The previous one definitely has a very wide applications too, but because of the technical nature of it, I guess you'd see it less. But moment sharing function, okay, is basically a ubiquitous topic, a very powerful topic, technique that is seen through in across many different subject area, right, including statistics. And so the outline of the topics, right, is as followed, right? We will define what moment sharing function is. We'll explain, right, the main use of the MGF, which is to, well, not main use, right? The reason why it's called moment sharing function, because you can use it to calculate the moments. But we'll quickly point out that, yeah, that's one good use, but it's not that common, or it's not that powerful, right? The most powerful technique or reason is because you can use the moment sharing function to identify distributions. And from there, right, we can use that to find the distribution of the sum of independent random variables. Okay, that's the sort of the crux here, that because the sum of independent random variables and the MGF structure has very easy connection, right? We will explain that. And finally, right, law of large number central limit theorem will be established, okay, via the moment sharing function technique. All right, so definition, right? Definition actually is simple. Moment sharing function is just expectation of e to tx, right? Whatever random variable x is. And so right away, right, even within this definition, several things can be said that should be said about it. Just because you can write down an expression doesn't mean it exists, right? Meaning that it could be infinity here, okay, for any value of t. So in that case, the moment sharing function does not exist, right? And even when it exists, it may only exist for some values of t. It doesn't exist for all values of t. Oh, by the way, right, I guess I forgot to mention, the moment sharing function, right, is a function of t, right? This variable right here, which is a number, right, a numerical value, whatever that is, right, a real numerical value, right? So it can be complex, but if you do complex value there, you talk about like the characteristic function. So it's similar, but not exactly the same, right? So basically, these are the technical aspects of it that, you should just kind of carry at the back of your mind, that not all random variables have moment sharing functions, and the moment sharing function doesn't have to be defined for all value of t. Now, this right here, right, in some other circle will be defined by the notion of Laplace transform. So if you have taken, right, a course in engineering or whatnot, 421, right, at Rutgers is engineering math, does go through Laplace transform, right? So that actually is the point here. So the moment function actually is the Laplace transform of the distribution function. Okay, so that's the the reason why it works as intended. All right. So the first business that we should go through is to find the moment functions of well-known distribution. And let me mention, right, at least for the final exam, right, these are things that are supposed to be memorized, right? The reason is you will see that the moment function, just like the mass function or the density, are signatures, okay, of a random variable, meaning that you recognize a random variable by these moment functions. Therefore, right, if you don't recognize these, you can't know, right, what random variable you're working with. Okay. And so let's see, right? These are actually problems of themselves. Let's look at this, right? So if you have a Bernoulli random variable, right, then e to tx will be e to t times p, right? Plus 1 minus p times e to 0, which is 1, right? So that's the moment function of a Bernoulli. Right? Any question about this? All right. So yep. Okay, so I guess here we start out with the normal first, right? This problem walk you through the derivation, right, of the moment function of a normal in general. But the first few parts, right, work with the standard normal, and then we make the conclusion about the general, right, normal by Z transformation. So let's see, right? So for a standard normal, right, the PDF is this. And so the first way, the first order of business, right, is to write down the expectation, right, which is the integral e to tx 1 root 2 pi e to minus x squared over 2 dx, right? So our business is to calculate this integral. Okay. Now, you might look at B and C already, right? But just in case, to give some idea here, right? Is this an easy integral to calculate? What technique will we use if you see this integral? Well, the answer is right. Integration by parts or U sub or all those techniques won't work. Okay, so you need, let's say, a new technique here, new-ish, right? And the technique is about completing the square, right? If you look at the exponent, right, which is this, then if you just, because, right, if you just look at the exponent, you got minus x squared over 2, right, minus 2tx. So what do we need to complete the square here? Sorry, right, actually, I mean minus 1/2, right? What do we need? We need a t square, right? And so, of course, you have to return the t square. So you have a t squared over 2 outside. And that would become, okay. Any question about this? All right, so the third step is basically use this, right? Use step B to calculate this integral. Because, right, basically then the integral will become e to the minus 1/2, right? X minus t squared 1 over root 2 pi, and then e to t squared over 2, right? Dx. And because the integral is with respect to dx, right? This term is a constant, so you can factor it out, right? And the claim is that you can evaluate this integral. How? How can you evaluate this integral? Well, the answer is right. What is the PDF of a general normal mu sigma square? If you have a normal mu sigma square, right? Then its PDF is 1 over square root 2 pi sigma squared e to the minus t minus mu squared over 2 sigma squared, right? And this is why you have to memorize all PDFs of well-known distributions, right? So compare this with this, what do you recognize? You recognize that this is the PDF of a normal t and 1, right? So if it's a PDF of a normal, then the integral will be 1. So the final answer here is e to t squared over 2, which is, right, the moment function of a standard normal. Right, any question? Okay, but right, notice that the calculation here used a simple PDF, right, to make the completing the square easy. But in general, we need to use this PDF, right, for the general normal. So, but we don't have to repeat, right, the same process for the general normal. By using the Z transformation, right, we can do something much easier. That's part D, right? Use the Z transformation, find the MGF. Okay, so how would that work? If X, right, is normal mu sigma square, right? And we already know that the Z moment function of a standard normal is e to t squared over 2. How would we use this fact and the Z transformation to calculate e to tx? What will we do? Well, the answer is, right, if X is a normal mu sigma square, then the Z transformation would say X is mu times a standard normal, sorry, sigma times the standard normal plus mu, right? And so it will be e to t mu, and then expectation of e to t sigma z. Right? How do we evaluate that? This, right, notice, I guess here I use e to tx, right, but it's really e to tz, right, where x is standard normal. So e to tx will give you e to t squared over 2, right? So here, right, this is like the moment-general function of a standard normal, but evaluate at t times sigma, right? So the final answer is e to the 1/2 t squared sigma squared. And right, usually you can just write one single exponential and add these two together. Okay, any question about this? So, right, for this slide, oh, I guess so. Here I just said right normal 0, 1, right? But we could have normal mu sigma square, right? That is e to t mu plus 1/2 t squared sigma square. Okay. Now, next one to look at is Poisson lambda. Right. So these are all the calculations, right? Okay. Now, so for the Poisson, right, it's kind of start out with the similar step, but we will need to use a different, I guess, approach, right? So we start out with the same thing, which is the writing down the expression for expectation, e of tx, right? But here, because the Poisson is a discrete random variable, it'll be a sum, right, rather than a integral. Okay. And now, how we would need to use some identity, right, to write down this sum. But how will we use this identity to conclude about what this sum value is? Well, we see, right, that first we can factor out eta minus lambda, right, and we have the sum. But here, right, we can combine, right, every term, right, raise to the power k like that. And so this sum becomes what? Right? Or here we written as like that. Okay. Any question? So right, the Poisson is e to a lambda e to a t minus 1. Okay. So this, right, we've done through calculation just to show you the calculation process. But right, the point is you will memorize these and just use them, right, and quote them just like the PDF and PMF, right, that we have derived, or expectation invariance, right, that we have derived in a previous lecture. Is that okay? Any question? All right. So now the moment-gen functions, right? It has the point of deriving the moments, meaning that the moment-gen functions can be used to obtain the moments, right, of a random variable. So how does it work? Well, it's pretty simple, right? If you differentiate the moment-gen function with respect to t, right, which is, I mean, that's the variable it has. But we use the partial notation here because, right, I mean, there's an x when you look at the expectation, right? There's an x. So I use the partial notation. But when you move the partial derivative inside, right, then you see that because you differentiate with respect to t, right, the x comes down, right, by the chain rule. But of course, right, observing that e to 0 is 1, then we see that if we plug in 0 for t, we got expectation of the random variable. So there you go, right? The first derivative of the moment-gen function evaluated at 0 gives you the first moment. And you don't have to stop there, right? The process will continue. You can just differentiate this expression again, which is the first derivative, right? To get to the second derivative. And another x will come down, right? And you got x squared. Plug in 0, you got expectation x squared. Right? Any question about this? And so, right, that's the name of the moment-gen function. That explains the name of the moment-gen function, right? That basically, if you differentiate the moment-gen function and plug in 0, right, then you got that moment according to the order of your derivative. Now, there's just one caveat, right? We kind of plug in 0 here as an easy explanation, but in reality, you may have to take limit. Right, you might have to take limit because the moment-gen function may not be, or the derivative may not be defined at the point. Okay, and there's some conditions that says that, you know, yeah, right, you so that you can take limit. But basically, if you cannot plug in 0 directly, you don't have to panic. A lot of times, right, you can just take the limit as t goes to 0 of the corresponding derivative. Then you will get the right moment, right, of that order. Now, the examples we'll go through, right, with the Poisson, with the normals, you don't have to take limit. You can just plug in value 0 directly. But this is just to, you know, let you know, like in general, plugging in 0 may not be feasible. In that case, you take the limit, right, as t goes to 0 of the derivative of the moment-gen function. All right, any question? Okay, so these are some examples, right? Again, so to not that, right? So notice, not that we need to use MGF, right, to find the moments here. We do know, right, the answers, but it's more like a verification, right? Where, okay, right, we use this moment change function technique to check that it's actually valid. Okay. For example, right, for Bernoulli, right, what is the MGF that we found? Remember? It would be P e to a t, right, plus 1 minus P, right? So we differentiate this with respect to t, right? So phi prime, right, at t is just P e to t, right? So phi prime at 0 is P, which is, of course, right, the expectation of Bernoulli, right? Again, not that we need, right, to have the moment change function to do this. So in that way, right, the remark here, it's not, probably not a practical way. It is a way, right? But you might have other more efficient ways to do it anyway, right? But at least you have, right, another method through the moment change function that's valid, that can be used. Okay. Any question? Now for these two questions, right? That would be the next one. So find this first and second moment, right, of the normal, and find the first and second moment, right, of the Poisson using the moment change functions, right? So first of all, right, the point is we have the answers known, right? This is not something that we don't know or need to find, right? But we just use the technique to verify that it works. So what are the first and second moments of the normal? Well, the answer is mu, right? And mu square plus sigma square, right? And so let's check if this corresponds to the answer by the moment change function method, right? The moment change function of the normal is e to t mu plus 1/2 t square sigma square, right? So what's phi prime? Well, here, right, you might need a good way to organize the differentiation. Of course, the chain rule happens, right? But there's an exponential, and so if we keep writing down the exponential, it might be tiring. So clearly the exponential stays the same, so we just call that phi sub x, right? Because that's the exponential. And then multiply, right, with the chain rule, which is sigma squared times t. Correct? And so, right, if we plug in 0, we get, well, we plug in 0 here, we get 1, right? And we plug in 0 here, we get mu. So phi prime of 0 is, all right? So that's correct. Any question here? Now, to find phi double prime, right? Well, right, we have to differentiate this. But differentiating this is actually this answer, right? So it's going to become phi xt square, right? Times mu plus sigma square t, right? That's differentiating phi x. And then, right, differentiating this, right, gives you sigma square. right? Sorry, did I say it wrong? Differentiating this, right, gives you the same answer here. So actually, because you get the whole thing here, right, and you actually get this whole structure squared, sorry, right? Because you get it again. So you get this whole thing times this, right? Okay. And so if you plug in 0, you get, well, again, right? This is 1. This is mu squared. And then, of course, the other one is sigma squared. So, okay. All right. Any question here? Okay. So let's move on to part B. Part B is the same thing, right? But now with Poisson. So let's ask ourselves again, right? What are the known answers for the Poisson? Well, for the Poisson, right? The mean is lambda, right? And the second moment will be the variance, which is also lambda, plus the mean squared, right? So lambda plus lambda squared. Okay. So let's verify this. What's the moment-Young function of the Poisson? Well, the moment-Young function of the Poisson, right, is e to the lambda, right? E to t minus 1. So if we differentiate once, what do we get? All right, if we differentiate once, right, we get e to the lambda e to t minus 1 times, right, the derivative of the top, which is lambda e to the t, right? And so if we differentiate, if we plug in 0, what do we get? Well, this, right, will return 1 to us. So actually, right, we should also maybe compactify it as phi sub x of t, right? Because that's easier to control. So if we plug in 0, right, phi of x at 0 will always give us 1. And then so the answer is lambda, which is the answer we know, right, that it is. Right. Any question here? Okay. What about a second derivative? Oh, so right here, we can use the same structure as in if we differentiate this, then we get the same answer, right, as this one. So it will be, right, this upon itself, which is lambda e to t phi sub x of t, the whole thing square, right? That's differentiating this, right? And then differentiating this, of course, you use just lambda e to t. Right. And so the final answer will be lambda squared, right? Because if you plug in 0 here, you get 1. And then this will give you just lambda, which is what we want. Right, any question? All right, actually, right, in this derivation, I made a differentiation error. It doesn't really affect the final result, but still an error, right? Can anyone see what that error is? In the second derivative calculations of both expressions here, right, I made the same error, which is what? Well, the error, right, is actually if I differentiate phi, right, I got phi prime, right, which is this, but it'll be phi prime times this. So the only thing that got squared is this part right here, right? Similarly, the only thing that got squared is this part right here, right? It doesn't affect the final answer. I just got my final answer correct, I guess, in a lucky way, right? Because for a moment Jang function, right, phi of the moment junction at 0 is always 1. So, right, if I put an extra square, it doesn't change my answer, but, it's still wrong, right? Because if I were to do the third derivative, then definitely that answer will be wrong. So, any question about this? Well, since you don't ask any question, let me ask a question then. Why is this true? Why can I claim that the moment Jang function of any random variable when I plug in 0 will give me 1? Why is that true? Well, the answer comes from the definition, right? Phi x of t is expectation of e to tx. So phi x of 0 is e to the 0x, but of course, right, that's 1. Any question? All right. So basically, right, that demonstrates the moment Jang functions, right, name, meaning that you can just keep on doing this, right, to find the moments. Now, it may be okay. I don't know, right? I mean, to keep differentiating this, and if you see the structure and the recursion, you probably can deduce the nth derivative formula, not painfully, and maybe the integration is harder, right, to find the moments by definition. So, but here, right? So the keyword is may not be. Who knows? Could be, could not be, right? But as far as I'm concerned, it's not really the reason why we study the moment Jang functions. Because, right? I mean, finding the moments, we already have some way to do so, right? It doesn't have to be that. Another way is good, but it doesn't have to be that essential, right? So what's the reason why moment sharing function is such an important topic? So the reason, right, is because the moment sharing function is unique, all right, for each distribution. In other words, let's say if you tell me, right, the moment you have a random variable, you don't tell me what it is, but you say that, well, the moment gen function of that one is e to the t times a number, right? Let's say you have a random variable x, right? You don't tell me what it is, but you tell me that its moment gen function is e to t 2t plus let's say 3t squared. Okay, like that. Then I immediately would be able to tell what random variable you are talking about, right? So what is this? What is the random variable that is being talked about here? The answer is it must be a normal, right? With what kind of mean and what kind of variance? The mean is 2, right? And the variance is 6 because, right, it's mu t plus 1/2 t squared sigma squared, right? So sigma squared is 6, right? Again, notice, right, that's a variance. So the standard deviation is square root of 6. Okay. So that's the point, right? Knowing the moment sharing function is equivalent to knowing what the random variable is. And that's why you have to memorize the moment sharing functions of well-known distributions, because that could be an equivalent way, right? That people describe the random variable to you. All right. Now, so we just want to quickly explain why this is true, right? Why this is true is actually this statement right here, right? If you have two random variables with the same moment sharing function, then they are the same random variable, right? I mean, same as in they have the same distribution, right? So we understand the difference between this, right, which has the notation x equals to y in distribution versus x equals to y, right? These are not the same thing. Do we understand the difference? So x equals to y in distribution would be like tossing a coin, a dice, right, for the first time, and tossing the dice for a second time. Okay. Then the tossing of the dice for the first time is equal in distribution, right, with the tossing of the dice in the second time. Or, right, you're just saying that they have the same distribution, right, which is 1/6 from 1 to 6. However, it's clear that the toss of the dice for the first time is not equal, right, to the toss of the dice in the second time, right? It's a random event, may not be equal. So when you say x equals to y, you're saying that they're exactly equal. You're talking about the same numbers, right? They're equal for all numbers, which of course, right? Then why do you invent another notation? But when you say x equals to y in distribution, you say that these can have different values, but their mass function or their PDF are the same. Or in other words, right, they behave the same probabilistically. Is that okay? Any question about this? Now, so why is that true, right? Why is this statement true? This statement is true because of the uniqueness of Laplace transform, right? I mean, that's the only way to explain it. So basically, right, this is a long way to say, right, if you know the MGF, which means you know the Laplace transform, then you must uniquely be able to identify, right, the distribution. Now, again, right, this is only true for the well-known distribution, right? For the not well-known, well, you can give a function, right? But who knows what that is? As in, like, you cannot give it a name because it's not well known, right? Okay. Any question? All right. So let's give you a quiz, right? And then we'll continue after the break. So I think let's have you do this one, right? For quiz, both part, but just do the first moment. All right. You don't have to find the second moment through a MGF method. All right. Any question before we take a break? Okay. All right. Let's continue at 7:05. Any question before we continue? Okay. So back to the lecture, right? So basically, right, identifying distribution is probably the most common and most powerful use, right, of the moment generating function. But I guess this alone may not be make it right that popular. Another, right, combining with another property is what makes it really popular, which is the MGF of the sum, right, of independent random variables. So as you can see, right, if you take exponential of a sum, right, it becomes a product of exponentials. And right, expectation of a product, right, is product of expectations as long as the random variables are independent, right? So couple these two together, give us a super nice result, right? That the exponential of the sum splits into product, and product, right, of independent random variable split. So basically, right, the moment generating function of a sum is a product of moment generating functions if they're dependent. And there you go, right? This, remember, right, that summing random variables is actually not an easy thing to do, right? Even if they're independent. Like if you don't believe it, right? Well, try to figure out what the sum of independent uniforms is, right? But this gives us a very easy way to find the moment generating function of the sum of independent random variables. Now again, right, the moment generating function, as powerful as it is in some ways still an indirect method, meaning that, right, if you don't recognize, let's say, the end result, right, you can find it, but if you don't recognize it, then it may not be that useful. But a lot of them are recognizable, as you will see, right? So at least for the well-known case, this property is alone very good for us to use. Okay, so any question here? So, right, let's use this to basically, right, establish these three most common results. That when you sum independent binomials with the same success probability, you get a binomial back, right? With the success probability being the same. So the claim is, right, x1 plus x2 here will be binomial, right, with success probability being the same, but the number of trials, right, just gets summed. For the Poisson case, you will see that x1 plus x2 will be also Poisson, but the rate got summed. And lastly, right, when you have normals, then you will get normal with the mean being sum and the variances being sum. Okay. Now, before you say that, well, isn't that trivial or whatnot, right? This is actually not trivial at all, and actually is special in the sense that, right? But basically, besides outside these three cases, I don't think there are other random variables that behave this way. Meaning that if you sum two uniforms, you will not get a uniform, right? If you sum two geometrics, you get a negative binomial. All right, things like that. So the distribution changes, right? Here is basically a closure property, right? You sum two distributions, you get it still stay in the same family. And that's what's special, right? And we will establish this by the moment generating function technique. Any question? All right. So right, that's actually these questions, right? So I guess, well, for part A, we found the moment generating function of a Bernoulli, right? But we did not find the moment generating function of a binomial. So let's do that, right? So if X is a binomial, then expectation of e to the tx, right, is a sum from 0 to n, e to the tk, right? And then p to the k, right? And 1 minus p to the n minus k, right? And then, of course, we will combine the k together, right, to give us p e to a t, right, times k 1 minus p, right, to the n minus k. Sorry, I forgot the n choose k, right? Okay, what would this sum become? This is a binomial expansion, right? Will become p e to a t plus 1 minus p, the whole thing raised to k power. Sorry, raised to n power, right? So that's the moment-Jane function of a binomial, NP. All right, any question? So now, right, if x1 and x2 are like this, then phi x1 plus x2 will be the product, right? Now, notice they have the same p, right? The only difference is the n1, n2. So when you multiply them, you will get n1 plus n2, right? But that's it, because, right, the structure of this is exactly the same as the structure of a binomial NP, with n being replaced by n1 plus n2. Therefore, right, we can conclude that the sum has a binomial n1, n2 p distribution. Right? Any question here? All right, so the Poisson we already established, right? The Poisson has the moment-Jane function as e to lambda e to t minus 1, right? So the moment-Jane function of the sum is the product, right, of the moment-Jane function. And right, so we have lambda 1 and lambda 2 here. Well, we multiply them together, right? Clearly, we sum the exponents, and e to t minus 1 factors out, right? With the end result to be lambda 1 plus lambda 2 e to t minus 1. Correct? But of course, right, this looks exactly the same as the MGF of a Poisson lambda, with lambda being replaced by lambda 1 plus lambda 2. Therefore, x1 plus x2 has a Poisson distribution with rate lambda 1 plus lambda 2. Any question? Okay. C, right, the same way. If you have normal mu sigma squared, right, then we have shown that is e to t mu plus 1/2 t squared sigma squared, right? So the product, right, the product of these two, right, with mu1 and sigma 1 and mu2 sigma 2, right, we just sum up the exponents, giving us e to t mu1 plus mu2, and then 1/2 t squared sigma 1 squared plus sigma 2 squared, right? And once again, this looks exactly the same, right, as a moment-Jane function of a normal with the corresponding parameters. Any question about this? Okay, so here, we just want to mention this, right? That basically the the notion, right, of moment function also extends to joint distribution, right? You can talk about moment functions of x and y rather than just x. But if you do that, right, then you have to be careful to use a vector for the scalar t, right? So before t was a scalar, right? But now you have to use a vector, namely two scalars. You can call it t1, t2, or you can call it s and t. In other words, right, each variable has their own scalar, right? X has s and y has t. Okay, it's a very common mistake to use the same scalar for both x and y. But if you do this, then you are talking about the moment function of the sum x plus y, not the joint moment function of x and y. Is that okay? And in general, right, you can basically do a dot product between the scalar vector t and the random vector x, right, to get the moment function of the vector x. Okay, any question about this definition? Now, why do we care about this idea? Well, just the same as MGF, right, uniquely identifies a distribution. The joint MGF uniquely identifies joint distribution, right? In particular, one thing it can do for you very well is that it can tell you when they're independent. So remember, right, independent, as you know it right now, has to go through the idea that the joint is a product of the marginals, right? That's the only thing you know right now. Joint as product of marginals. But of course, right, this requires you to check that this is true for all variables, meaning that you have to know the abstract structure of the joint PDF or the PMF and the marginals PDF or PMF, which could be painful, right, to establish. The using the joint MGF moment function gives you an alternative by saying, right, that the moment function, the joint moment function, is a product of the individual moment functions. Okay. Now, is this easier or harder? It depends, right? Depends on the case you have. So it gives you another way to do it. That's all there is, right? Because at the heart of it is the calculation of this guy right here, the joint MGF. Might be painful to calculate, but it doesn't require you to look at the joint PDF on its own, right? You can just look at the joint MGF, and sometimes like the integration or depends on the information you have, right? Having the joint MGF is kind of like more direct, but it's just something to know, right? It doesn't have to mean that this is easier or harder than the traditional approach of proving that the joint is a product of the marginals. Okay. Any question here? But in general, right, the idea is the joint MGF uniquely identifies a joint distribution. But we don't have that many well-known joint distribution like we can name it besides the joint normal, right? So that this property is not invoked as often as the MGF of a single random variable. Okay, so that's just more like an FYI, right? So here, right, is one of the payoff, right, of moment functions besides establishing distribution of the sum. MGF is probably the most elegant way to prove asymptotic result. In other words, right, MGF can be used to establish all big three results that we mentioned so far in this class: law of large number, central limit theorem, and Poisson approximation, right, to the binomial. And let's just mention why this works. Why this works, right, again, relies on the fact that the moment-Jane function, right, uniquely identifies the distribution. So we can establish, right, the moment-Jane function of whatever we need. And then, right, we can establish that the moment-Jane function of this object converge to the right moment-Jane function of the target as n goes to infinity. So instead of proving this complicated probabilistic limit, what we do is we take the moment-Jane function of the terms and then take the limit as n goes to infinity of those moment-Jane functions and show that it converges to the right target. Okay, so that's the key. Any question? Right, and this is just stating that of the last result, right? The Poisson approximation to a binomial. Okay, so let's see how this works. Okay, so question number 5 here, right? Basically shows you, right, how to do, asks you to do all of this by moment-Jane function technique. So the first result, right, the law of large number, basically says the average, right, the empirical average converge to the true average as n goes to infinity, right? This sum right here converges to mu as n goes to infinity. Okay. Now, so for part A, right? Let me see here. Right. So for part A, we want to express the moment-Jane function of this sum in terms of the moment-Jane function of the individual term. Remember, right, the xi are IID. Independent, identically distributed. Therefore, right, they all have the same MGF. Okay, because they're identical. But more than that, right, because they're independent, the moment-Jane function of the sum, right, is a product of the moment-Jane function. Right? But they're all the same. So it's the same moment-Jane function raised to the nth power. All right. But now what? It's not that, right? It's divided by n, right? It's not just this, it's divided by n. So how do we handle that? Well, the division by n actually can be handled quite easily, right? If you have the moment-Jane function of this, right, divided by n, evaluate at t, right? By definition, is expectation of e to the t over n times the sum, correct? Because the division by n, right? N is a scalar. You can call it to be the same in the same location as the t. But if you look at it as a scalar, then it's really the moment-Jane function of the sum evaluate at t over n. Do you understand? So basically, right, this is p sub x at t over n, everything raised to n power. Any question about this? All right, so let's show you the magic, right? Or what is at stake here. What is at stake here, right, is the claim that the sum, right, divided by n converge to mu, right, as n goes to infinity. Okay, that's what at stake. In the language, right, of the Momentan function, then this, right, is a Momentan function of this. The Momentan function of a single number mu, right, is, well, expectation of e to t mu, which is e to t mu itself, because mu is not random, correct? Mu is just a number. So what is at stake here is to show that this object right here somehow converge to e to t mu as n goes to infinity. That's a law of large number. Okay. And what is strange here? What is the most strange, right, is the fact that somehow, right, phi sub x here of t over n can be any function, right? Because x can be any random variable. So why is it that doesn't matter what x is, they all converge to the same e to t mu? That's what is at stake. But this is actually not, let's say, not surprising, because the law of large number claims as much. The law of large number claims that doesn't matter what the xi here is, right? The empirical average will converge to its true distribution, true mean, which is mu, right? So if it's Poisson, it still converge to lambda. If it's exponential, converge to 1 over lambda, right? It's binomial, converge to n mu, np, right? Basically, the distribution doesn't matter, right? Whatever the distribution is, it will converge to its true mean as n goes to infinity. Is that okay? So the task of all of this is that somehow to show that by the Momentan function technique, we see that this doesn't matter. The structure of phi of x doesn't matter. Okay. Any question about this? Now, how can we do so, right? How we can do so is by part C here. By basically, right, analyzing the Momentan function into its kind of a Taylor expansion structure. All right. And you will see that the Taylor expansion structure gives us, right, the universal structure that we need to analyze the conversions. All right. Okay. So basically this mysterious function, right? And notice, why do we care for the Taylor expansion here around t equal to 0? Because as n goes to infinity, right, t over n goes to 0. So that's why the Taylor expansion will be relevant to look at, or as a relevant substitution for phi sub x of t as n goes to infinity. Phi sub x of t over n. Do you understand? All right. And so, right, so here, right, this is a Taylor expansion, right? And of course, I hope we remember, right? Phi sub x at 0 is 1. We talked about that. Phi prime of x at 0 is mu, right? And but here is t over n, right? Because it's t over n right here. I guess t over n, right? And phi double prime right, is mu square plus sigma square. Right, 1/2 t squared over 2n. So that's a Taylor expansion for phi sub x at t over n around as n goes to infinity. Any question about this? Okay, right. Well, is this enough? Well, this is enough, right? If you know the identity, that is. This one right here, right? 1 plus x over n, and doesn't matter what the higher order terms is, raised to the n, the limit of this is e to x as n goes to infinity. Okay, so let's take a look at that. Okay, so now, right, we have this, right, raised to n, which is this raised to n, right? So you see, if you compare this, you see that here x is t over n, right? And then we actually don't need to care about this. We wrote it down, but this is the higher order term in terms of n. Right? So according to this result, then the limit as n goes to infinity of this raised to n power is e to the x. Sorry, I'm talking nonsense, right? X is mu times t. Sorry, right? X is mu times t, right? So the limit of this as n goes to infinity is e to t mu. Okay. Any question about this? All right. So for this part B, right? Part B and part E, right? Use the same idea, right? Part B and part E use the same idea, right? So I will just show you the result, right? To spend time kind of talking about the other problems. But it basically uses the same idea as part A, right? You write down the moment-Young function, right, of the sum using the product and then replacing the scalar as appropriate. You use a Taylor expansion, right, to turn that into a 1 plus something structure. And then you just identify that something to conclude that the right limit works. So for the central limit theorem case, right, which is this term, okay, this is why I don't want to kind of go through the whole derivation because it's rather long. For the central limit theorem case, right, you see that you got the product, right, of the moment-Young function, which has this scalar part that comes out because they just, numbers. And then you got the moment-Young function evaluate at t, but dividing by sigma over root n. Okay. So basically, is this function, right? It's very similar to the law of large number, right? But instead of dividing by n, it's divided by sigma over root n raised to n power. So it turns out, right, that the scalar here is a nuisance. So we assume that, mu equal to 0 for the central limit theorem, right? because the central limit theorem actually starts out with x minus mu. So this guy has mean 0 anyway. So we can replace that with another term called x tilde, right? We can replace this with xi tilde, where expectation, right, of xi tilde is equal to 0. So we don't have to deal with a nasty limit, which is this one, right? We can eliminate this term because we assume that mu is equal to 0. And we can, right? It's not without it doesn't lose any generality when we do so. So anyway, right? If we eliminate this term, we see that we will deal with the structure like this. And if you use a Taylor expansion, right, you see that actually you exactly miss the first term because it's 0. The mean is 0. But the second term, right, squared, exactly gives you t squared over sigma squared times n, right? And this combined together gives you 1/2. The 1/2 of e to t squared over 2, which is the moment-Young function of a normal. Do we understand? Any question here? All right. So this is actually the most complex case, and it just has to do with the fact that you have to deal with the sigma of root n. That's all. But if you really want to understand how the central limit theorem works, then it's worth your while to look into this and see how the root n, right, gets squared, and that gives you the right limit. Okay. But now let's move on to the Poisson case. With the Poisson, right, notice that the binomial itself, right, has a structure of a sum, the sum coming from the Bernoulli, okay? And even better yet, it has the 1 plus something here. So if you try to turn that to a 1 plus something, right, you can divide by, right, look at this one, and then look at everything else, divide by n, right? And exactly this right here is the, e to t minus 1 that you need with p times n is equal to lambda for the Poisson case. So everything, right, relies on that structure where you have 1 plus something over n raised to n converged to e to x, even for the Poisson approximation. Okay. Any question about the last one right here? Okay. All right. So the last couple of problems, right, is just really applying the MGFs, right, to solve something, right? And it emphasized on the fact that you can use MGFs to identify distributions. Okay. So here, right, you have x and y given by this, right? And you want to compute the joint MGF of x and y. Okay. So remember, right, the joint MGF of x and y is expectation, right? E to the s times x plus t times y, right? Which is the double integral of e to s x plus t times y, and then 1 over root 2 pi, right? E to minus y, e to minus x minus y square over 2, right? So here is a question. what do we want to do first? Dx dy or dy dx? That's actually where the identify part comes in, right? We want to do dx dy or dy dx, or does it matter? So the answer here is you should do dx dy, because if you look at, right, for a fixed y, then this part right here is the moment, is the PDF of a normal with mean y and variance 1. Okay? And so if you do dx first from minus infinity to infinity, then the integral of e to sx, this part and this part, you know what the answer is. Right? That's the identify part, right? The answer will be the moment-gen function, right, of this random variable evaluated at s, which is e to the s mu, right, plus 1/2 t square, sorry, s square sigma square. Sigma square is 1, so it's just s square. And then, of course, right, integrate with e to ty dy. Sorry, there's an e to minus y, right? Do we understand? But then, right, the last part is pretty easy because this 1/2 s square is a constant, so it comes out. The rest, right, is just the integral of e to the s plus t minus 1 times y, right, which of course is like that. Right? Any question? Okay, so now part B asks you to compute the individual, right, moment-gen functions of x and y. All right. So what does that I guess require? That requires, right, that we need to find the marginals of x and y, right? And then you use the moment-gen function technique to find it. So again, right, let's take a look at this joints PDF right here, right? If you integrate the x out, right, might look scary. But if you integrate the x out, what do you get? If you integrate the x out, you get 1, right? Because that exactly is a PDF of a normal with mean y and variance 1. So the answer here is just e to minus y, which is the PDF of y. Right? Any question about this? Okay, now that seems easy, but what happens if we integrate the y out? Sorry, now y goes from 0 to infinity, right? How will we integrate this to get the density of x? What can we do here? All we can do here, right? Remember the theme is I guess recognizing MGF is more like it. But because this is the normal, right? So this is the PDF of the normal. Then e to the minus y, right? You can look at this as the right PDF of a normal would mean, I guess here you integrate out the y part, right? So you can look at this as a PDF of a normal would mean x invariance y, right? So this is a fixed x changing y. But still, right, because you do e to the minus y here, this is the MGF of that normal evaluate at -1. Okay. Now, what's the MGF of a normal like this? It'll be e to t mu, right? Which is either tx, but t is -1, so it's e to minus x. Okay. And then what? Plus 1/2, right? T square sigma square. But sigma is 1, and sigma is 1, right? And t is -1, so it's just plus 1/2. No. I think I'm talking nonsense. Give me a moment. Let me get my thought back. No. This is nonsense. Sorry. This is complete nonsense. The reason, right, is because here we integrate from 0 to infinity, right? If we were to integrate minus infinity to infinity, then we can use this technique. But we'll integrate from 0 to infinity, so what I'm saying is complete nonsense. We cannot view this as a normal density because we'll integrate from 0 to infinity. Nope, that's out. All right. Anything else at our disposal to calculate this? No? Oh, you know what? uh Gosh, I guess I had a lapse in my thinking. We already calculated, right? We already calculated the joint MGF. We already calculated the joint MGF. So for the marginal MGF, right? The joint MGF, remember, is expectation of e to tx, e to sx plus ty, right? So the marginal MGF, of course, you can just plug in, right, 0 for the corresponding values here, and you got the other MGF, right? So I guess I have a complete lapse of thinking. The marginal MGF can be obtained easily from the joint MGF by plugging in, right, s equal to 0 or t equal to 0. That's really it. Okay. And there it is. Right. So actually, it's a lesson, right, to be learned that if we go through the marginal route, it'll be very hard to calculate this because the marginal of x is not nice to calculate out to begin with. Okay. Any question? All right. So, wait a second. I thought we have more problem. Well, that's weird. This is it. I thought we have one more. I have one more problem. Well, I guess no, I don't. So these are all the problems I have. So that's so weird. I could have felt I have more. But anyway, this is it for now, right? Any question about anything we covered today so far? Yeah. So I really think I have one more problem that is somehow lost in the process. So, well, if anything, right, there's one more problem. I'll have to look. I think there's something when I compile this problem set that I did not have. We'll cover them right next time. One more problem. Okay. So if there's no question, let's end maybe 4 or 5 minutes early today, and I'll cover this extra problem right on Monday. Okay.
Have a good one.
Yeah, you too.